Hello, everyone. My name is Tino Heimhuber. I'm a postdoc at the Water Research Laboratory in Sydney, Australia. So my background is actually in remote sensing. So I did my PhD on large-scale remote sensing of surface water dynamics in the Murray-Darling Basin. And I really like to think that remote sensing actually runs in my family. So this is an image of my hometown in southern Germany, of my grandfather, who used to be a photographer, and in fact, so have been all of his sons since then. And I really think that, photography and remote sensing is quite similar in that essentially all we're doing is taking electromagnetic radiation and transforming it into an image, although for different purposes. And so what we then do in remote sensing is that we use this image information on a pixel by pixel basis, typically, to infer different characteristics of the land surface based on the spectral signature of things. And so maybe a little bit of a background of how InletTracker actually came about. So about 3 years ago, I was working on a guide document called Climate Change in Estuaries as part of my postdoc. And then I was approached by my colleague and surfing buddy, Kilian Voss, who is the developer of COSAT, which is a really cool open source Python tool for mapping shoreline change dynamics anywhere in the world. And he told me that, hey, look, I know you're working in estuaries. This tool is really picking something up there. I think you should have a closer look. And so he really sent me down this massive rabbit hole for a couple of years, of which I luckily eventually emerged out of. So I followed his advice because I was curious, and I had a bit of a closer look to see if there's potentially something in there. And I quickly found that we can definitely get a good signature of inlet openings. But I also quickly found that it was going to be a very difficult task, because if you look at what's the pixel size of the sort of longer term satellites like Landsat, you can see that you're often going to get mixed pixels. You have different water colors, waves, white water, all sorts of weird stuff, which makes your life harder. You can have channels that are quite small compared to the pixel size, or you can have shadow casted by headlands, which is quite common as well. And so I knew we needed a really smart algorithm. So I went to the drawing board, did some deep thinking, and thought that what if for each image we could find or identify the transect that traces perfectly actually from a point in the ocean to a point inside the inlet along the inlet channel, we could then extract spectral indices along these transects, and we should get a class separation between open and closed inlet states, right? So I did some deep digging. I think this was actually during the lockdown last year, and I came across this least cost path finding algorithm. And so essentially what we do is, again, we use a spectral index that amplifies water over other classes. And then we try to find a connection between 2 points, say A and B. That's not a straight line. Instead, we're looking for something like this, where essentially you're accumulating the least amount of cost or elevation gain along this transect. And so what this algorithm does is it takes the spectral index as a cost raster where water is cheap and sand is expensive, or other classes are expensive. And then it iteratively routes through the grid until it finds the path of the cheapest connection. And so this was really cool. So it took me a while to implement this in Python, but eventually it kind of did what it was supposed to do. But we quickly found that even though we could set up these seed and receiver points quite easily, it would often shortcut across the berm, because the shorter distance led to a lower total accumulative cost. So this was a big problem. but I found that we could solve this by essentially exponentiating the cost raster, so making the water even cheaper and the sand and other classes even more expensive, just by exponentiating the grid. And this is what you can see on the right, and this worked really well. So essentially, we found a way for the algorithm to do exactly what we wanted it to do. And so you can see here, it traces the inlet channel almost perfectly in this example. And so there was one more step, though, that we needed to take for identifying whether an inlet then on a given image was open or closed. And remember, everything had to be fully automated. So we did this by doing a bit of a transect analysis, and we quickly found that the dry sand has a really stable value. And whenever the transect crosses the inlet, it dips, and we can look at, or we can take this difference between the bottom of the dip and the dry sand value as an indicator for the state of the inlet. And so if we look at a closed image, you'll quickly see here that indicator becomes 0, essentially. So that's how InletTracker was born. Here's a high-level overview of the entire method and tool. And what it uses is the Landsat 5, 7, 8, and Sentinel-2 satellites, which have a 16-day and then eventually a 5-day revisit interval of the site and a 30 and 10-meter resolution, respectively. And so this is important to keep in mind. So in the earlier years, you're going to have to work with lower resolution, whereas in later years, you get more images and a better resolution. So we then set out to do a very large validation experiment for 12 IOCE sites in Australia. And this has only just been accepted for publication in geomorphology, which is pretty exciting. So here's an example, or 3 example sites from this paper. And this is a bit of a lot to digest, but essentially we're looking at the data from the InletTracker tool, which are these dots, and then compared against 3 independent validation data sets, which is an analyst going through the images and saying it's open or closed, the degree of tidal attenuation inferred from water levels, and an observational record from the council, which are these gray and white shaded areas. And you can see that for Daras, we're getting a perfect agreement across all data sets, which was super exciting because we never thought we were going to get that good. Conjola as well, really good performance. So this is a predominantly open system, as you can see here by the amount of blue dots. And Lake Coila, which is a predominantly closed system. But you can see that even these relatively short openings, we typically are able to capture them well with the tool, right? So this was super exciting to be able to remember this is fully automated. This doesn't involve any manual steps whatsoever. The tool also readily integrates a global tide model so that for each image, you know exactly what the level of the oceanic tide was. This is important because here in this example, we're showing 2 images taken only 5 days apart, but during low and high tide. So low on the left and high on the right. And you can see this massively influences the spectral signal over the transect, right? But what this allows you to do is to be smart and work with that information and potentially only use images taken during low or only during high tide, depending on what you're trying to achieve. We can, of course, also then apply the tool to other examples, such as the Rio Grande River that closed for the first time since records in 2002, or barrier island breaches that are caused by hurricanes in this example. And then, you know, potentially it closes again, or this one, it stayed open since the breach. But again, the tool provided a really robust approximation of these dynamics. So where to from here? So first of all, this is an open source community tool, and we would really like to see this tool being picked up by the community and being developed further. So if you jump to the tool's GitHub page, which will provide the links, of course, you can download the tool, the entire Python code here, and there's a step-by-step instruction on how to install it. And it's really easy to set up new sites. You just set up a shapefile in QGIS, and the tool will do all the rest for that. And I will also try to upload a detailed step-by-step sort of instructional video of actually how to install the toolbox. But this is beyond this talk. So I encourage you all to have a look and really think how you could apply this tool in your context, because we would love to see this being applied more. We are already starting to use the tool and apply it to coastal engineering for different consulting projects. I'm also started to collaborate with Sarah McSweeney. We're applying the tool for about 50 or so sites around the world, because we want to look at a large study where we're looking at global trends and patterns, both across space and time, in the opening, closing dynamics of different IOCEs. And we really encourage everyone to get in touch with us if you want to get involved with this study. I think we can find some really cool patterns there. I'm also putting out these weekly animations. I'll show you one right after this called, you can find them under the hashtag Water from Space Weekly. And I'm also trying to build an extension of the tool called Wetland Tracker for tracking the hydro period of wetlands. So just really quick, I'm running out of time here. This is a Water from Space weekly animation using InletTracker for a site that's about 3 hours north of Sydney called Farquhar Inlet. And as you will see just now, this is a really dynamic inlet. It migrates quite a lot north and south. So if you pay attention here to, or in the 90s, it eventually started a really fast southward migration down here. But you can also see that the tool picks up the state of the inlet really well. So remember, blue is open, red is closed. So it really didn't close for the first sort of 20 years, as you can see here on the time series, but then it did briefly close in the early 2000s, but not for long. And then if we fast forward here a little bit, you can see what you're going to get. You get a 30-year plus time series of, you know, open versus closed inlet state, and you also get this shapefile with all of these transects, so you can actually start doing some morphodynamics kind of analysis, you know, migration speeds, width of the inlet, etc. And that concludes my presentation, and please get in touch if you would like to use the tool and require more information. And thank you for tuning in.